Alright, what's up guys? In this video we're going to pick up with some vector calculus here, and we're going to be using the divergence theorem to calculate this flux integral here. So we're asked to use Gauss's divergence theorem to calculate the flux integral, which they give us here. And they say basically S here is the boundary of the box that's given by the following. And we have our vector field here, which is F. And our vector field has three components. So we need to use the divergence theorem, or Gauss's divergence theorem is another name for it. So we've done videos on this before. So let me just quickly remind you what divergence theorem is. And it basically allows us to relate surface integrals and triple integrals. So the Gauss's divergence theorem is the surface integral f dot n ds is equal to the triple integral. D is the region, and then we'll have our three-dimensional divergence. So that's the divergence theorem. Okay, so all we really need to do for this is, first of all, we need to get the divergence of this vector field. We'll go ahead and get that here in just a second. And then we can set up the triple integral and evaluate it, and that will give us our flux. So let me just quickly remind you of the three-dimensional divergence, if you've forgotten all about that. The three-dimensional divergence of a vector field. So remember, that's div f, where f is the vector field. And remember that the divergence of a vector field, the three-dimensional divergence, is just the dot product of the del operator in f. And it's just going to be equal to the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. Okay. So let's go ahead and get our divergence with our vector field here. So we'll have div and our vector field here obviously has three components, so we'll need the partial with respect to x for our first component, which is x squared plus yz. Then we'll add that to the partial with respect to y for the second component of the vector field, which is y minus z. And then we'll add that, sorry, make sure the camera stays still. Then we'll add that to the partial with respect to z, and we'll take our third component of this vector field here, and we'll need to take the partial with respect to z. So that's 2x plus 2y plus 2z. So that's the first thing we got to do. We got to get this three-dimensional divergence first. Okay. All right. So what are we going to get for that? Okay. So let's take our partial derivatives and see what we get. So what's going to be our divergence here? So it looks like we're going to end up having 2x. So we take the partial here with respect to x. That means we're treating the other variables as constants. In this case, y and z is treated as a constant. I need to take the partial here with respect to y for y minus z. That's just 1. So this is 2x plus 1. And then I'll take the partial with respect to z over here for 2x plus 2y plus 2z, which we know is just going to give us a plus 2. And so therefore, we can say that our divergence of this vector field here will be 2x plus 3. Okay? Alright. So now what we'll need to do is set up the triple integral and evaluate it. So we'll go ahead and do that next. And I'll just Let's see, I'll set that right there. I'll look back at it when I need it. Okay, so again, all we're really looking for at this point, all we're really trying to do is just get our, evaluate our triple integral now. So let's go ahead and take care of that. So we now have the three-dimensional divergence, which was 2x plus 3. And now if we go back to it says this is the boundary of the box. S is the boundary of the box given by the following. So these are going to be our limits of integration. So when we set up the triple integral, we're going to evaluate the triple integral dz, dy, dx. So let's go ahead and set that up. So since we're integrating it dz, dy, dx, one of the most important things that you need to do for these types of problems is make sure that you're lining up the limits of integration correctly with the appropriate order. So since I'm doing this dz, dy, dx, that means we're integrating with respect to x last. So the limits of integration for the outermost integral here are going to have to be from 0 to 2. Then I have my second integral here. Again, dy is what we're going to be integrating with respect to second, so that's going to be from 0 to 4. And then we're integrating with respect to z first, so this is going to be from 0 to 1. And then we'll have 2x plus 3, and this will be dz, dy, dx. Alright, now it's just a triple integral. Alright, so remember what we do for triple integrals. We basically work our way from the innermost integral to the outermost one. In this particular case, again, we're going to integrate with respect to z first, and then we'll work our way through the other variables. So from 0 to 1, 2x plus 3 integrated with respect to z. So clearly there is no z anywhere in here, so that means that we're treating, not only is the 3 a constant, but the x is also a constant, or the 2x is also a constant. So this is just going to give us 2x plus 3 multiplied by z, evaluated from 0 to 1. Okay. And when we substitute in, notice that we're just going to get 2x plus 3 because 2x plus 3 times 1 is just 2x plus 3. Substituting in 0, that's just going to be multiplying that by 0, which will give me 0, so I'm not really subtracting anything away. So now we'll be down to our double integral now. And it's going to be 2x plus 3. And then this time it's going to be dy dx. So as you can see, and I've said this in plenty of videos, triple integrals don't tend to be very difficult to evaluate. Most are very, very simple. And quite frankly, I've done more work evaluating just single integrals than I have ever for most triples. Triples are typically more difficult to actually set up than they are to evaluate. Because if you notice here in this particular video, I mean, there's no integration by parts, there's no U substitution, there's no trig substitution, there's none of that stuff going on here. It's just some very basic integration techniques that we're applying here to get the answer. So now we need to evaluate from 0 to 4. We need to integrate with respect to y now. So from 0 to 4, we got 2x plus 3. This time it's going to be with respect to y. So again, as you can see, there's no y contained anywhere in here. We're treating x as a constant, so everything here is treated as a constant. So 2x plus 3, and it's going to be multiplied by y, and it's going to be evaluated from 0 to 4. So we can clearly see that this is just going to end up giving us, and we can bring the 4 to the front. Remember, multiplication is commutative, so sticking it at the back is the same thing as sticking it in the front. So we'll have 4 times 2x plus 3. And obviously substituting in the 0 just gives us 0. So, you know, we just end up with our 4 times 2x plus 3, which we'll be integrating with respect to x now. So we're now down to our last integral, which is from 0 to 2. And we're integrating with respect to x, 4 times 2x plus 3 with respect to x from 0 to 2. Okay, so the 4 is a constant. So from 0 to 2, we integrate 2x dx, and then we'll add that to the integral from 0 to 2, and we're going to integrate this constant 3 with respect to x. So the integral from 0 to 2, 2x dx, again, use the power rule, and if we substitute in our limits there, it looks like we'll just get a 4. And then here we have the integral from 0 to 2, we got 3 dx. Again, we evaluate this, we'll get 6. Just basic integration there. So it looks like we'll have 4 multiplied by 4 plus 6. 4 plus 6 is 10, so if we multiply 4 by 10, we'll get 40, which will actually be your answer. So your final answer for this, when we evaluate or calculate the flux integral, the answer here is just going to end up being 40. And that's your solution. Okay, so let me know if you have any questions about this. I'll be more than happy to talk about it, and more than happy to explain how I got my answers. Alright guys, I will see y'all next time.